Okay, so we'll do three things. First is a chapter overview. Second is the theory. And third is an overview of the practicum, which is the code actually implemented in Earth Engine. So this chapter introduces characteristics of remotely sensed imagery, imagery from satellites, and how they can be examined in Earth Engine. We have two main learning outcomes. The first is to understand spatial, temporal, and spectral resolution. And if you're already familiar with GIS, so for example, using QGIS or ArcGIS, you'll probably have a handle on these concepts, but if you haven't used them before, this is your introduction. And then second, to use the Google Earth Engine console to gather information about a digital image. So, if you have experience with other GIS systems, this will be how you can get that information in Earth Engine. And then if you haven't used these systems before, you'll be able to see and learn about where to find this information. We assume for this chapter that you know how to navigate among different Earth Engine result tabs. And we also assume you know how to visualize images with a variety of false color band combinations. And these were covered in chapters F1 and F1.1. I will mention quickly that for the practicum, because the previous chapters have already done a really great job of explaining how to choose an image from an image collection and how to display that image. I'm not going to be going into much detail about those things. And I would just encourage you that if you find yourself lost in those operations or those functions, that you go back and review F1.0, F1.1, and F1.2, because those chapters really do a great job of laying all this out. So quickly, the theory. If you recall, last week we talked about Earth Engine image collections. Andrea walked us through that. And image collections have many different images in one large data storage structure. And they include information about the location, date collected, and other properties of each image. So this week, we're going to kind of take that knowledge and really turn it into knowledge that you can apply to your own work. So there are lots and lots of different types of satellite imagery and other digital images that are available, but not every data set is appropriate for every analysis. So things you need to consider when you're doing your own your own work, you're applying what you're learning in this book to your own research or your own projects. You want to be considering things like the spatial, the temporal, and the spectral resolution, what data is included, what the accuracy is, all sorts of different aspects. So just as an example of this, one study found that higher resolution, so 1 meter pixels, this data produced higher accuracy land use classifications, but the lower resolution data set, so 900 meter pixels, was less costly and required less analysis time. So these sorts of trade-offs are kind of always going to be present in your work, and understanding them, understanding how to get this information and make these comparisons is a really critical piece. Andrea and I wanted to include this diagram. It's from the University of Maryland, and it's kind of a good overview of why you might need different types of imagery for different work. So if you compare something like looking at emergency response, so this might be the immediate after effects of a hurricane, of a fire, of a flood, any of these sorts of very important but very localized impacts. So you need small spatial resolution, so lots of pixels for one area, and you need short temporal resolution. So these events happen quickly. So you need information that happened in this time period when the flood happened, so you can assess the emergency response needed. On the other side, for example, you might have something like climate change analyses, in which case you're looking at large scale. So you probably are doing, continental or global analysis, and you're looking over many years. So you're looking at change. So just these two types of different research can start to highlight the different types of satellite imagery you might need, the different types of, the different types of properties of those images that you'll need. So let's dive into the practicum. Before we dive in, I am going to make a quick mention. So I think Jeff has shared with you how to access the book scripts, and these links are also present in the book text themselves. And it's this link here, which someone might want to, Andrea or Jeff, if you could share that in the chat, that might also help the participants. And I'm just going to make a quick note, which is that when you click this link, you should see the book repository pop up in Google Earth Engine. And if you don't see it, there is a, there's a refresh button next to the new button in your scripts. And if you hit this and wait, it will pop up. So we're going to talk first about the search bar that Google Earth Engine has, because it's a really valuable way to find information about different data sets that Google Earth Engine has available to you. So this search bar up here is the main search bar. And so if you have a specific, for example, data collection that you have in mind, this is a great way to find it. So we're going to search for Landsat 7 collection 2. And we'll see a couple of things pop up. First, you can actually see that there's places. This is really valuable if you're looking for a specific place on the globe, so a specific town where you're doing your analysis or something like that, but it's not actually helpful here. So next, let's look at the rasters. And here is where we see all of the different rasters that fit the search terms that Google Earth Engine has available show up. So there's a couple of different things that you can do from this window, and we're going to cover a number of them, but I always suggest, when in doubt, just click the button. There's a lot you can find just by exploring, and there's not a whole lot you can do to mess it up. So first, there's this import button. So if you click this, if you know this is the data set you want, it will just import it straight into the script that you're currently working on. Super easy. But say we want some more information. So we can click on one of these, and it will actually pop up with this overlay window that has more information. So we see that there's a couple of important pieces of information. The first is this collection snippet. So this is a piece of code that you can copy. And you can then copy and paste that into your script. There's also on the right-hand side here, a whole bunch of information about the actual data set itself. And you can also get band information, and this is super important. I always go here when I'm, trying to pull bands for analysis. It usually has some really excellent information about, it has the resolution, it has what they're called, which is what I always forget. And it also has wavelength information. So all of these things, super important, and we'll get more into them as we move through this lesson. So it also has some of the image properties. So these are specific pieces of metadata that you can pull. And again, we'll get more into that further into this lesson. And some image collections also have terms of use. So these are, any limitations that are placed on the use of the data for your analysis. So Landsat 7 is, courtesy of USGS. So it is public domain, which is great. So there's also a pop-out button, and it's really easy to miss. It's actually this little button right here in the corner. Hopefully you can see my mouse here. And if you click on this, it will take you to a new window. And is that still sharing? Hopefully that's still sharing. Okay, great. Thank you. This will take you to a new window that has a lot of the same information that we just went through. So the description, bands, etc. But it has it in its own window. So you can have the, you can close the overlay window and still see the information about the data set, which I find very helpful. It also has a little snippet of code down here. So this code snippet can really help you understand, for example, how to pull the data set, how to filter the data set, different things you can do with it. It's just a little bit of an introduction to that specific data set. You can always copy paste this code. You can always open this code in the editor. The Earth Engine team has really done a great job with all of their data sets that are in the catalog in terms of having this information available. So there's a lot more that you can also do with this. And I leave some of that up to you. But I do highly encourage exploring this, the data collection. If you hit the more, you can see a whole list, and this open in catalog button, I think Andrea talked about last week some. And this open in catalog button will actually take you to the Earth Engine data catalog. Sometimes it takes a little while, so we're not going to go into that too much right now. But Jeff, did you want us to pause after every section or pause at the end?
Yeah, I think pausing after every section turns out pretty well, because then there's sort of manageable chunks and gives you a moment to breathe as well, because I think it's got to be pretty draining to do.
Perfect.
All right. So
well, then I'll pause here. The next section, and in this next section, we'll talk about spatial resolution. So when we think about spatial resolution, this is really the amount of the Earth's surface that's covered by a single pixel. So I believe in previous chapters, we've talked about how raster data sets are structured. I believe, and correct me if I'm wrong, that was F1.1. And so now we're going to think about, okay, so how much of the Earth does that one pixel represent? So we're going to do this by comparing 4 different data sets from the MODIS data set, which is what we call a coarse resolution data set, to the NAPE imagery, or the National Agriculture Imagery Program. So this is US only, but there are other similar data sets in other locations. The US just happens to make theirs freely available, so we use it a lot. And this is 1/2 to 2 meter resolution. So, it's pixels are about, you can kind of think about what that would look like just by, drawing it out kind of for yourself, right? It's about this big, as opposed to 500 meters, which is, the better part of a block. or well, a lot bigger than a block. So this is going to be checkpoint 1.3a. And let me just go ahead and load this, and now we'll run it. And this, I will point out, nothing in this checkpoint is a function that you have not learned about previously. So I'm not going to spend too much time talking about each of the individual functions. We'll really focus on talking about the spatial resolution. So when we run this checkpoint, it's doing a couple of things for us. It's importing the 4 image collections and then mapping them. And then it's also pulling a couple of pieces of data. So if we first look at the console, we can see that the 4 pieces of information that it's pulling are all labeled scale. So I'm just going to look at one of these data calls, and here for modus. And if you want to follow along in your own code, this is lines 33 through 35. So we can see that what's happening here is we're taking our modus image, we're selecting a band, and then we're calling the nominal scale. And that we're then printing that to the console. So this is the same function, same call that's being done for all 4. And it gives us what the scale is for each of the data sets. So now I'm going to show you what these look like. And I'm going to use the ability to turn on and turn off different layers. So we'll start with modus. And as you can see, the scale is, the exact scale is 463 meters. It's actually because of the projection. It varies a little bit in terms of how large it is, but roughly 500 meters. And you can see that the pixels are very, very large. If we then turn on our TM, which is the Landsat 5 thematic mapper, this is a 30-meter pixel. And you can see all of a sudden the airport kind of comes into view, right? We go from, let's see, I can't really tell that there's an airport there. I can tell there's water over here. And, these are urban pixels, to being able to see the airport. And I see the question pop up in chat about the modus pixel slanted. It has to do with, I think we put an explanation of this in the text, but it basically has to do with how the satellite traverses the Earth and how it's processed. So they use a very specific projection that results in that appearance. Yeah. And so the, even finer grain still is the Sentinel-2 multispectral instrument. This is a 10-meter pixel. So now if you think about it, going from a 500-meter pixel, which, half a kilometer is a huge difference or distance, down to 30 meters, down to 10 meters. And then when we zoom in here to the airport and let everything load quickly, you can start to see, detail for the building. You can start to see a lot of the differences between the runway and the grass between the runways. You can actually even see the reflectance of an airplane. And then if we turn on the nape layer, which is a higher resolution still, you can see really, really detailed information about the airport. So you can see individual planes, you can see the different jetways, bridges, all of this information, vehicles, really, really detailed. So you can think about when each of these 4 scales would be useful. And there's actually, there's scales on either side as well. So, there's information that has an even coarser resolution than the MODIS data. And there is information, most of it is commercial, so you have to purchase it, that starts to get down into, you're measuring it in inches. It's sub-meter resolution. So. All right, so the next piece of resolution that we'll talk about is temporal resolution. And temporal resolution refers to the revisit time. And this is basically how often a satellite passes over the same piece of ground. And this is usually measured in the number of days. And it's kind of the frequency of pixels in a time series at a given location. That's the easiest way that I find to think about this idea. So we're going to look at 2 different temporal resolutions. The first is Landsat, which has a 16-day revisit time. And the second is Sentinel-2, which has a 5-day revisit time. So this will be checkpoint 1.3b. Let me just switch back to Earth Engine right now. Oops. Oh, and this happens sometimes. Okay. So if this ever happens to you, because I just had this happen and I'll show you how to fix it. If it becomes all map and you can no longer see your code, it's at the top of the screen. There'll be this kind of thick band with the dots in the center, and you just have to pull that back down. Good. All right, so we'll go to checkpoint 1.3b. And once that loads, I'm just going to go ahead and run this. All right. And so this includes, just as a quick reminder, or if you haven't looked at the code before, the way we structure these checkpoints is that they're sequential. So checkpoint 1.3b includes all the information from A, or generally includes all of the information from A, in addition to the new information presented in B. So we're just going to scroll down here to the B checkpoint where we're exploring temporal resolution. And I'm just going to quickly go over the chart function, because I believe this is covered more or in more detail later. But briefly, what this code is doing is we're first printing the Landsat revision or revisit time here, where it says Landsat 5 series. And you can see this is an image collection, and it features 6 elements. So basically we have said, in this location, between these dates, get me all of the images that fit those criteria. And there's 6 images. And it basically means that between those 2 time periods, the satellite revisited the area 6 times. But that's pretty hard to think about, right? It's actually a lot easier to view and think about the temporal revisit time, or the temporal resolution and the revisit time, if we create a chart. So that's what we do in this next piece of code here. So to create a chart to see Landsat 5 16-day revisit time, we use the UI chart image series. And we take the image collection, we select a band, we filter the dates, and then we tell it where we want these to be pulled from. So this piece here is basically saying these 6 images, please. And then we will graph them. And then we use the set series names in order to name the series, name the line, basically the data that we're going to chart. So the second piece of this, and I believe in the chapter we go through what happens if you don't use this, essentially. But the second piece of this is to define a chart style. And this basically just makes it easier for you to look at it. It makes it easier for you to share the charts with colleagues. It's not super necessary if, for example, all you want to do is quickly look at the data. But this really does help. So we define the chart style using a variable call, and we define 3 pieces of information. The first is the horizontal axis. So we're going to call that date. So that's the title argument. The vertical axis, or the y-axis, we're going to call the near infrared mean. And then finally, we're defining how the series, so again, that series that we called NIR, the near infrared, we're defining how that appears. So with all of those pieces put together, we can then apply this custom style properties to the chart by using the set options function. So we call the save chart, and then we apply the chart style to it, and then we print it. So this is the printed chart. And we can really see here the 16-day revisit time. And you can see how each of those 6 images that were pulled up when we just said, hey, give me everything between these dates in this location. And then we got this list here of features. We can see now how those are plotted, and we can see how much time is passing between each of them. So this is a really useful approach if it's difficult for you to, and as it is for me, to see how or like when temporally the different images are in relationship to each other. We can use the chart function to graph this quickly and easily, and be able to really see that. And for me, this is a lot easier to understand than a list and trying to, like dig into each of these and figure out where in the properties the date is here, and then, so on and so forth. So we also do the same thing for the next instrument. So for the Sentinel-2, which has a 5-day revisit time. And again, using the chart image, again, selecting the near infrared band, which for Sentinel-2 is band 8. And the because we are selecting band 8, that is what it is graphing as our as our y-axis. So our near infrared mean value is that value. And then we have the dates again as the x-axis. The other really nice thing I will show you about the charts is first that you can mouse over each of the values and it will tell you what the value is. So for example, this point, this was an image from July 18th, 2020, and the near infrared value is 1,814. The other nice thing that you can do is there's again a pop-out window. So in the upper right-hand side here, you can click on this and it will actually create a large version of the chart. We'll use this functionality a couple of times throughout this lesson. And I always look for that little pop-out icon is the same one that we also saw when we looked up the imagery. And we could create a new window with the information about the imagery. So Earth Engine tends to have this functionality, and if you look for it, it's a very small icon always, but it is frequently there. And from that window, we can also download it in different formats if we want. So this is useful for, again, sharing information with colleagues. All right, so Section 4 of this chapter gets into spectral resolution. And this goes back to what I was saying a little bit about the type of camera that's taking the pictures. So spectral resolution is the number and width of the spectral bands for which the instrument is taking measurements. So if you recall, the electromagnetic spectrum, including the portion of the visible light spectrum that we see, is a continuum. And the sensor measures generally not the whole continuum, but it measures pieces of it. So how many of these pieces it measures, how wide they are, how and other properties there are what we call spectral resolution. So most satellites have what we call a multispectral sensor. So it has three, it takes the roughly 3 to 10 pieces of information from that continuum of wavelengths. But there are also what we call hyperspectral sensors, and this is up to hundreds of slices, generally very narrow slices of that continuum of wavelengths. So in order to think about this more, we're going to compare the spectral resolution of two sensors, MODIS and the EO1 Hyperion hyperspectral imager. So from the name, you can tell this one has a lot of bands, whereas the MODIS is, I'll call, more typical. It's a multispectral instrument. So just switching back to Google Earth Engine, we're going to pull up the C checkpoint and run it. And again, it includes the code from A and B and then adds the code from C. So we're just going to jump there. And so here's the start. So again, there's a couple of different ways that we can access this information about any given data set, any given sensor. So the first one is to just say, hey, Google Earth Engine, can you tell me what the band names are? And then print that list. And so that's what we have here with the MODIS bands, and it's a list. But we can also tell that not every one of these bands, just looking at the name, is actually, an image. It's not part of the camera. It's not, the information that the camera took. It's metadata about that image, right? So including information about QA is usually some measure of quality. And then, for example, day of year or azimuth. So we can see that only some of them are actual information about the wavelength. So then we can say, okay, well, we really only want to look at the information about the different wavelengths. So let's select the reflectance bands only. So that's what we're doing here. We're saying only the surface reflectance bands. Let's not pay attention to the other types of metadata that are associated with the images. So like we did before, we're going to create an object that has customization parameters for the chart. So this includes the title, horizontal and vertical axes. We're going to say we don't want a legend, please and thank you. And then also specifying how large we want the points to be. And then we're going to make the chart. So again, we use the UI chart image regions call on those selection of bands for the SFO point, which is the point we've been using, that is the airport in San Francisco. And then again, we're saying, please use the options we just specified. So that's what we see as this MODIS spectrum here. So if we look at that at a larger scale, we can see the measure of reflectance in reflectance units, and then how much reflectance for each of the 7 bands. So, but now if we want to do the same thing for the EO1 bands, and we say, please give me the list of names, as we did with the MODIS bands, we can see there's literally over 100, right? So it just keeps going. So we're going to need to create a new set of options here, which is what this piece of code does. The main difference being the title name. And then we'll create a chart again. So let me just hide this list of almost 200 different bands. And when we call this chart, again, we're saying use the UI chart image regions for this image, which was the image we chose before, and using the options that we just specified and printing the chart. And so you can actually see how many, all the 100 different, or almost 200 different bands. And this is where that pop-out button is really useful, because you can't see the individual pieces until you do so. And then you can really explore better all of the different, hundreds of different bands and their different reflectance levels. And if you wanted to, for example, chart each band to the precise wavelength, that's when I would suggest looking at the information that is provided by Google Earth Engine, as well as by the satellite information website itself. So, okay, so for the fifth section here, we're going to talk about per pixel quality, and we got a little bit of a preview of this for the MODIS data when we saw that QA band. But we're actually going to look at the Sentinel-2 MSI instruments. Instrument is redundant there. QA60 band. And this contains information about the surface reflectance quality. So there's a couple of different things that could, if you think about trying to take a picture from a satellite of the Earth's surface, there's a number of different things that could make your picture less good. And the QA bands try to encapsulate and kind of put together that information and provide an estimate of how good the information for each pixel in the image is. And this can be extremely useful. A lot of times with the pre-processed data sets that most people will be using, the processing has already accounted for this issue. But if, for example, you're creating a like a composite where you're taking multiple images from, say, a 3-month period, maybe it's the dry period for the area that you're studying, and you want to say, okay, I want the best pixel for each of these. This might be important information. Other things that'll be important are how many clouds are there? And these are all things that we'll talk about in future lessons. But just as a reason why understanding that pixel quality is important, there's a few examples. So I'm going to go ahead and switch over to our Earth Engine checkpoint 1.3D and go ahead and run this. Oh. Interesting. All right, hold on a second. Yeah, I gotta refresh the page. There we go. Nope. All right, we'll try that again. There we go. All right. So again, scrolling down to the end of this checkpoint, just to look at the pixel quality. What we're doing here is first filtering to get a specific MSI image. And then what we're going to do is display the image as a false color composite. And as a second piece, map just the QA60 band. So that is our quality, that's our quality band. So using just the layer controls, what we can see is first, we can see that here's the image that we've seen. Actually, I'm gonna go ahead. Here's that MSI image that we've seen before. And now we're going to go ahead and turn on the quality visualization. And what you can see here is that the quality has a lot to do with here, where you're actually seeing clouds. So if you look at this piece in the upper left-hand corner, we can see that there's some clouds and some atmospheric interference there, and that's showing up. And if you remember the inspector tool, so you can click on the map to get the values. And so if we click in that upper left-hand corner, what we can see is that QA band has a specific value, and it's actually 2 seconds. There's actually, basically, there's only 3 values in this band. So if we click on the different colors, we'll be able to see that. So this gray piece here has a QA60 value of 1024. The white areas have a value of 2048. And the black areas have a value of 0. And if you remember, those values might sound familiar. They're basically binary. And it's basically 3 different categories. So no issue, and then 2 different types of issues. And so this would be a really great time if you wanted to know, and we actually explore this in the text of the chapter. We're running kind of short on time, so I won't get too much into it here. But the different types of issues which have specific values, all of this information will be available in the metadata, in the information about the satellite and the satellite bands. So either available through the satellite's website or through the Google Earth Engine catalog. All right, now for the last portion of this chapter, and things we've kind of chatted about previously, but we'll talk about more in detail right now. The metadata. Understanding how to access the metadata is really important. As we've been talking about the different aspects of, the temporal resolution, the spatial resolution, and which wavelengths are present, which aspects and measures of quality are present, many different aspects. All of this is important. And if you're kind of running your analysis, you need to have information about these in order to make good choices for your analysis. So here, in addition to this, the band imagery, the per pixel quality flags that we've talked about, Earth Engine also provides you with substantial amounts of metadata associated with each image, and in some cases associated with each pixel of each image. But we can easily print this information to the console for the single image. So let's go ahead and do that now. So moving on to our E checkpoint, let's go ahead and run this data or run this code. And we'll switch back to our console. Go ahead and turn off some of these layers just so that stuff loads faster. And then we'll scroll down to the end of the code. So this is a pretty simple checkpoint. All we're going to do is pull the metadata and then show you how to access a specific piece of that metadata, which is important sometimes. For example, if you want to, say you have an image collection and you're trying to figure out what which images you want to include in your analysis. You might want to say, okay, well, only give me the images that have this much or less cloudy pixels. How do you do that? Well, the first thing you can do is say, please print all of the metadata for this image. And you don't have to, this is just a name. If you say print the image, it will print your image, not the actual picture, but the information about the image into your console. So if we start expanding this, we can see that. We can see what type of thing it is. We can see what it's called. We can see our list of bands. But importantly, we can see this list of properties. And as you can see, this image has 66 properties. And if we look through them, this is the metadata. So here's the cloudy pixel percentage, as well as information about, for example, it passed the general quality check. It passed the geometric quality check, which it provides information about the mean incidence azimuth angle for the different bands. It provides information about, solar irradiance, sensor quality pass, what orbit number it was, what the direction of the orbit was, lots and lots of really important information depending on the type of analysis you're doing. Most of the time, you don't need to know what the mean incidence angle was, but when you do, you really do. So back to our question about cloudy pixel percentages. So we can see that the property name here is cloudy underscore pixel underscore percentage, all caps. So the next thing we can do then is say, please, for this image, please get me this value, the cloudy pixel percentage value, and then print it. That's what we can see here, printed in our console as the last value. And so this same idea is something we'll use a lot in the future. As we start to get more into analysis, particularly in I believe it's the F3 chapters, where we start talking about pulling in multiple images in order to do regressions and classifications, as well as in F4, when we're talking about interpreting image series, a lot of these cloud issues become very important, even for very basic analyses. So here's your sneak peek of that, and here's your a way to check the metadata for the images. And I highly recommend you explore this and use this command for other satellites so you can start to understand and see what all of this information is.